Okay, so few part already described what I was saying about here. So you have to find out the value of a, b and c. So you have 1 2 3 4 5 equations, so you have 3 unknowns, so not necessarily we need to use all the equations. So first equation you have x, there is no x, so we are not using it. For the second equation y0 u0, so you can get u, a capital A should be 0. And for the third one you can use it, but we just wait, because otherwise you don't have the, if you put the double derivative, in this case you will have the constant values, so we just keep it, or leave it, later on we can think about it if we need it or not. So for the fourth one, yeah, you will get this one. If you put y is equal to delta, u is equal to capital U, you have this equation. And similar way, if you put y is equal to delta and du by dy, you consider the derivative of this equation, you have this. So you have two equations here, including b and c. Just solve these two, and if you solve it, probably you will get b. Oh, cannot write. Just write it down. Okay, maybe b is you can get 2 capital U by delta, for an example. You cross check. Okay, I'm not sure that we will get this value or not. And c is minus capital U by, sorry, minus capital U by delta square. So if you substitute this equation, I mean the values for a0 in this b and c, and you reshuffle, usually you will get this one. You will get this equation. Okay, is it clear till now? These things I already explained before, but I'm explaining it again. Any questions? Okay, so now you already have this equation. Okay, so then we continue with this one, calculate the displacement thickness, because this calculation already done by few students already. We check it out already, so that's okay. And what is the expression for momentum thickness? Also the students already solved. Shape factor also the students solved. Okay, few of your friends already solved. Remember that whenever you calculate the delta, okay, so we have this equation. Sorry, this is delta star, right? Displacement thickness. So 0 to delta 1 minus u by capital U, or u infinity dy. So just put the value here. Okay, so you always get delta star as a function of delta. You will also get the theta as a function of delta, and then if you make the ratio, you will get one constant value. This is always true. You cannot have any variables in the shape factor. Okay, so delta star is also a function of delta, that is the displacement thickness depends on the boundary layer thickness. Momentum thickness is also depends on boundary layer thickness. So for the momentum thickness, you already know the relationship is something like that, u by capital U, and then 1 minus u by, I'm not having the space here, okay, u infinity and then dy. Okay, so main thing is you need to substitute this u by capital U here. So you will have 2 y by delta minus y by delta whole square. Just simplify it and you can solve the problem. Okay, so now this d is new one. Okay, so you must go through the von Karman integral form from my video or from my explanation. You must understand that one, but there is some derivation, but you need to know one formula that we use, that is the wall shear stress. So wall shear stress can be calculated in two ways. Okay, so one you already know from Blasius form. One is from Blasius form, that you know that this is for Newtonian fluid. We know this is equal to mu, and then we have du by dy, right? Y is equal to 0. This is the definition of wall shear stress. So this is wall shear stress because I put y is equal to 0. On the other hand, in the equation what is said, sorry, in the questions what is said here, already cross. Okay, said that the shear stress equation tau following both von Neumann and integral and Blasius form. So they ask you just to write down the equation. So equation will be this one, and for the von Neumann integral, the equation is rho capital U square, then you have d theta by dx. This is the general expression. The students who are not watching my videos, you will not understand what I am saying. Okay, you must, yeah. Okay, what do you want to say? Yes.
The slide number 5 from the one karma.
Integral. Okay, hold on. I will open it. Wait. Slide number 5. Yes.
This is regarding rectifying the mass flow rate for the ME and R and NBC, right?
Yeah, this one is for mass flow rate. You are right. So we just consider here in, and we have out. So we try to find out what is the BC, because it will balance, right? So in is equal to out. So in this case, in will be total in will be m dot in plus m dot BC is equal to m dot out. So m dot BC will be m dot out minus m dot in. So if you have these two term, here is we have one term. So this term and this term will be cancelled out, and you will have only this term left.
And then we substitute the mass flow rate into the law equation, right?
Can you say again, or you write down, because your voice is broken?
Oh, sorry.
Or you slowly speak, then I understand.
We substitute the mass flow rate into the Newton's law equation, right?
Yeah. Then after that we got the equation. So we substitute this one, this equation. This This is third law, okay? As I mentioned. Yeah, but
the expression is different after we substitute. The u become u squared.
no. Okay. So don't confuse about this one is mass flow rate, okay? Small m. Similarly, if you have mass flow rate, then momentum flow rate you need to multiply by u. Okay, so this this one is just demo that if you have the mass flow rate in this way, similarly if you have the momentum, just multiply by u, but u not velocity. In this case for BC should be us, and for the within the boundary layer it should be small u, because u will change, right? So that's the thing. So we have the momentum. Don't confuse with the momentum, capital M, with the small m, that is the mass. This one is momentum. This one rate of change of momentum, okay? This is not rate of change of mass. This is capital M. You know the Newton's third law. So rate of change of momentum, it should be equal to applied force. So applied force should be rate of change of momentum. So how much change we have? Out minus in minus BC. Okay, it means the out minus in, because we have two in. Okay, so I just continue. Okay, so that's how you need to ask questions, otherwise it could be difficult whether to understand, whether you are understanding or not. Anyway, so those students who haven't gone through the von Karman integral, you must go through, because you have the quiz. And so probably I will put the quiz later on, okay, maybe during weekend or maybe tomorrow. So I will not disclose the things. So you should be at least you should solve this problem. So what I'm saying here, this is they just ask you to write the equation. So this is from the Blasius form, this is from the von Karman integral form. So you can get these things later on, okay, in the derivation, so I'm not going to explain the things here. So what is said here in the problem, next one is you need to find out the boundary layer thickness, that is delta, in terms of x, u and mu. You need to find out the delta in terms of x, u and mu. So how to find out the delta? So in this case, how about the equation number 1? This one, equation number 2. So you need to find out, first of all, these two are equal, right? So I can write this right hand side should be equal to this right hand side. So what you need to know here, you need to know du by dy, right? You need to know du by dy at y is equal to 0. So you know that du by dy we already got it before, okay, or you can say that you know that in this case u by u infinity is equal to 2y by delta, okay, minus y by delta square. So here what you can write, small u, so don't be confused, okay, the u and capital U. So u infinity and this one, right? So if you differentiate this one, du by dy, what you will get, u infinity, and then you differentiate this one. So what you will get, 2 by delta du by dy is 1, right, minus 1 by delta square should be 2y. So you have this expression, right, du by dy. So but you need du dy at y is equal to 0. So du by dy at y is equal to 0 should be, you just put the value of 0, y is equal to 0. So what you will get, u infinity, then you will have 2 delta, right? So now you already have this expression in form of u infinity and delta. So du by dy is actually 2u by delta. Okay, please forgive me if I do any mistake in integration, because I'm just solving it right now here. I could do mistakes, so please cross check. Okay, so you already have du by dy in this case, and what else you need? D theta by dx. Okay, so how to get the d theta by dx in this case? So you just find out the theta first. What is the theta? So theta is 0 to delta. You already know u by u infinity 1 minus u by u infinity dy. So you already know that u by u infinity already have the values, right? So just put the values there, 0 to delta, you just put the values, and then 1 minus, put the values, okay, and then you integrate. You already know how to do it, so you already calculated, I think, the theta you already got it right before. So you will have, if you do the integration, in short, you will have some value delta, any value, okay, something by something, okay, you will have something is delta. So you will have some constant, I mean in this case you will have some constant, that is a function of delta. So in this case, so d theta by dx, just you write in this way, d by dx of this theta, okay. So theta you need to just put here, and you cannot differentiate because you don't have any x, so you just put theta here. Theta means in this case you will have, sorry, what you will have in this case, you will have only a function of delta, right? Maybe some constant, I just write a, maybe a delta. So now you already have this value, d theta by dx, you already have du by dy. What you need, you just substitute these values. So if you substitute this value, what you will get, because you have these two equations, right, Laplace form and then von Karman integral form, so both are representing wall thickness, wall shear stress. So in this case you just substitute the value and then equate these two equations right hand side. So you will get something like u capital U, you can put u infinity is better, otherwise you will mix the small u and capital U when you will derive. So always try to put u infinity or us just to make sure that you will not mix up the small u and capital U. So this one is ddx, is theta value, as I said, for an example this is capital A, constant some value you will get, I'm not sure what how much you will get. Then you have the delta, and that's equal to, and we have what else, we have mu, sorry, in this case we have mu, and then we have du by dy at y is equal to 0. In this case you have u infinity and maybe 2 by delta, because we already got the value, right, u infinity 2 by delta. So if you have these two equations, what you have now, so you have u infinity, right? So this one you just shuffle it. Okay, I just consider ddx. In this case you have capital A, for an example some constant value is delta, should be equal to, we have mu in this case, sorry, mu by rho. Okay, and then you have u infinity will cut down and you will have u infinity here. Okay, and then you have 2 by delta in this way. So now if you integrate both sides, if you do the integration on both sides, what you will get? You will get some constant value a delta is equal to, in this case rho by mu should be nu, right? So in this case you will get rho by mu, for 1 minute, rho bl by mu. Okay, you just need to replace nu is equal to mu by rho, right? Am I right? Yeah, that's okay. Sometimes you need to help me, okay? Sometimes I need to think all the things. So mu by rho is actually nu, right? Are you there? Is it okay? Because I'm not seeing you, so I'm not sure who are watching, who are sleeping. Is it okay? Okay, please respond, okay? Yes, no, okay. Okay, thank you. Because it's difficult to I just teach and then I don't know whether you are understanding or not. So mu by rho is nu, and then you have the u infinity, and you have the integration 2 by delta, right? So if you have the integration, integration is actually with respect to x, right? So in this case, if you integrate, these are all constant values, okay? So I just erase this integration and I just put the value x. I have the integrating constant, but that integrating constant should be 0 actually, okay? So you can avoid for now being. So what you will have, so I'm not sure this a value, but when I calculated, it was like 2 by 15, okay? I'm not sure, please do the calculation. So just for make the things like how it looks like, I will put the value, but I'm not sure. So you will have this one, okay? So what you will have now, you will have cut down these two and you will have delta square, right? And then what you will have, delta square should be, you will have mu and u infinity and x. Am I right? So if you have this one, where is the 15? You should have 15. So your delta will be root over of 15, but you will have some value. I'm not sure, again I'm not sure whether it's 15 or any values, because it just roughly I say the value of a. And then within this one, you can manipulate this one. How you can manipulate? So x means what? X means root over x, is it right? So we have inside x, right, root over, and then we multiply x and divided by x extra. So if you do so, what you will get, you have root over 15 or whatever value you will got. So you reshuffle, what you will get, mu is there, root x, so I'm sorry, you need to multiply by root over x, root over x. So root over x will be cancelled out. Okay, and then we will have the inside, we will have, hold on, maybe I do any mistake. Oh, this is okay. 1 minute. We should have u infinity, and you should have x here. If you want to have x in this case, okay, got it. Sometimes you need to, okay, so what you need to do, I need to make the Rx Reynolds number. Okay, so if you want to make the x here, if you want to make x here, so of course you need to put x on the upper side, right? So already you have root over x, and then again you are putting root over x. So root over x and root over x, you will have x outside. I hope you understand, or you can understand it in your way, should be okay. So mainly what I'm going to say, root over 15 is 3.87 something. I'm not sure. You just put the value something you will get, and you will have the value x, and then you will have root over of Rex. So in this case, Rex is Reynolds number, is local Reynolds number. So you know that Ux by mu is Rex, it's opposite. So your delta should be this value. Okay, so most of the time you will have the delta theta, whatever it is, you have some constant and multiplied by x divided by root over of Rex. So this constant sometimes vary, depends on the situation, depends on the physical problem. Okay, so that's how we can derive. So here is a tricks, you have to tricks it here. Okay, so now I go to the problem, what he said. Okay, so it asks you to delta in terms of x, u and mu. So x, u and mu in this case already delta in terms of x, u and mu. Okay, so already you have this expression here, delta in terms of x, u and mu. And then it said that okay, it haven't said anything, but you can actually reduce the value to the Rex. Okay, so if it doesn't say that, you just keep it like this, keep it until here, should be okay. Yes, please.
How does du dy becomes 2 over delta after we differentiate?
How du by dy here?
Yeah. What after differentiate it becomes 2 over delta?
This one. So you have this 2 delta, 2 by delta, and then you differentiate this one. So dy by dy is 1. And then in this case 1 over 2 delta, sorry, 1 by delta square, you have to use y square. So you differentiate y square, it will be 2y. So y is 0 because the condition is like this. So if you put y 0, you have 2 by delta. We are differentiating. Delta is constant.
Y equals to 0 is the boundary condition, is it?
Not boundary condition, this is the condition for wall stress. At the wall stress, this should be y0 because considering the stress at y is equal to 0. This expression is for wall stress. This expression for wall stress. It means the position where y is 0. You can say is boundary condition, but is actually the definition of the wall stress. Is it okay?
Yes,
so that's how you get this value. But as I said, normally we can extend this one up to here. So next thing, frictional resistance CF, okay, in terms of x, u and mu. Again same thing, x, u and mu. Okay, so how to get the frictional resistance, or in this case is local friction CF. There are two things, okay, one is local friction, that is C small f, another one is average friction, that is C capital F. Okay, so here we are considering the C small f. So how we can get this? According to the definition, you know that the frictional coefficient occurs, the friction occurs due to the shear stress. Okay, so the local frictional coefficient is actually nothing but is a non-dimensional value of stress. So tau divided by half rho u square, that is u infinity square. This is the definition of local frictional stress. So is actually the stress, but we make it non-dimensionalized, so it becomes local skin friction coefficient. And this one is actually for local, we put it like the tau. So tau in this case, according to the it said like von Karman integral form, we can represent the tau is rho u infinity square d theta by dx, right? And then we have half rho u infinity square. Just substitute the value of tau. So then you will have, if you simplify it, what you will get, 2 d theta by dx. Okay, so if you have d theta by dx, you already have d theta by dx calculated before. So here you have d theta by dx, right? ddx of some value of delta. Okay, so you already have this value. So for an example, let's see, I'm not sure the values. Okay, please try to calculate by yourself. In this case, your d theta dx, what we did last time, if you remember, we put dx and we put the value of theta in terms of delta, right? So theta in terms of delta, what you got, how much? For an example, you got 2/15 of delta. Example, okay. So how you got? You go back. Okay, you just put the u by u infinity is equal to y by delta. You integrate. So that's how you will get d theta by dx. If you get d theta by dx like this, then you know that you also got the delta in this way, right? Delta is how much? Root over of 15 rho x theta x, or u infinity. Or you can substitute this value, or you can substitute the value of delta is like this. Okay, this is the value of delta, is up to you. You want to put it this one, should be okay, but more or less you need to change it to in this form. So first of all, they say to express in this form and then change it to this form. So you just put the value of delta in this case. So ddx of course you have 2 by 15, delta is root over 15, or I don't know how much you had. Then you have, okay, root over of mu x, root over of mu x divided by u infinity. So you can see, so I'm not sure, just you simplify it, these are constant, okay, these are constant, and you have a function of x here. So you need to differentiate with respect to x, and if you have differentiated this one, what you will get, 2 by 15. You need to know the shortcuts, okay, so otherwise you will be puzzled. So for an example, mu and then u infinity. Okay, I'm not sure about this value, again I'm saying again and again, please recheck by yourself. So you need to find out ddx of root over x, right? So what is the ddx of root over x? Who can say? Who can say what is the value ddx of root over x? Nobody knows. You forgot. 1 over 2 root x. ddx of root x is 1 over 2. Yeah. So this will cancel out, right? Again, I'm saying I'm not sure the values. Okay, for me is cancelled out. I don't know the actual one. Maybe I do some mistake anywhere. But follow the strategies. The strategies are important. Even you do the miscalculation should be okay, but you should follow the strategy. So in this case again, so what you have 1 over root over 15 for an example. Okay, now you have mu like this, right? Okay, so if you have this one, then it said that I don't know, I missed out somewhere, I don't know. So CF in terms of x, u and mu. So CF in terms of x, you should have somewhere ax, okay?
Doctor,
Yes.
I want to ask, how can 2 over 15 times by set 15 becomes 2 over set 15?
Where? Here.
Yes, yes.
15 means what? Root over 15, root over 15. So 1 root over 15 is crossed down.
No, but I calculate the value is actually 2 delta over 15. And it is true that your example is 2 over 15 delta.
This one.
Yes, yes.
You mean this one? You mean?
Yes, yes.
This is coming from delta value.
No, I mean, how can 2 over 15 times 15, square root of 15, become 2 over,
root over 15.
square root of 15?
Okay, so root over 15 can be written as like this. This is root over, sorry, 15 can be written is as root over 15, root over 15. It means root over 15 whole square. And then you have root over 15, so it's crossed down. Okay?
Okay.
So you just practice, okay? So it means d theta by dx, if you differentiate, you will have the values, okay? So then you need to simplify it, and then you will get the CF, but you should have extra x. I don't know where it's gone. Okay, so you should have extra x. So after you calculate the d theta by dx, okay, I will try to solve other problems, okay? Then you put the values there, and then you have 2 theta by dx, right? So you have to find out d theta by dx in this case, this one. So ddx of this one, delta, you put this value. Did I miss somewhere? I don't know. Something I missed out. Mu x, and then root over ddx of this all constant. ddx of root over 1 by 2 root x. So it should be something is wrong. Vx. Anyway, so I will solve another problem. So let's see over there. Okay. So for now, this one is root over of Rex, but you should have some Rx x value. Okay, please try to solve it by yourself. Maybe I missed out somewhere. There should be some Ax. So basic thing is you just differentiate this one, simplify it, and put it in this equation. Then you will get the CF. This CF. Okay.
Doctor,
Yes, it is.
we getting the Reynolds number, right?
Yeah.
Isn't it in a class?
This one. We have two form, right? One is Vx by nu, right? This is a local Reynolds number. If you put x, this is x. We call this local Reynolds number. So that's why in this case you have the opposite of it, right? So that's why I put, oh yeah, it should be like this. You mean that, right?
Okay, yeah.
Yeah, now it's okay. So as I said, maybe I can do some mistakes. So please just take the guideline and solve it by yourself. Even the root over 15, I'm not sure. So okay, So I'm not sure about the values. Just I roughly calculate and to show you how to get these things. But again, according to my understanding, we should have some x here somewhere that is missed out. So I will try to solve another problem. Okay, but so far, if you solve it properly, I think you should get it. But just note it down, that you can cross check that where should have you should have the x and not, because it said that represent CF in terms of u and mu. That is okay. That we already did. CF in terms of, if you just put the value, we have u naught, u infinity, we have x, we have mu. So that's okay, no problem, satisfied. And then the next problem is said local friction CF in terms of Reynolds number. So in terms of Reynolds number means you have to compress or concise the form in terms of Reynolds number like this. Okay, so that's also answering of the next question. And the last one, frictional drag. Okay, so frictional drag in this case you can see is the integration of the force is stress multiplied by area, right? So if you have the frictional drag, so drag will be frictional stress multiplied by area. That's the thing. So in this case, the expression already given for your understanding. So normally is a stress. So we have the stress, then area, cross-sectional area. So we need to integrate along the length. So we have the dx. So it's 0 to L over the length. And we have the area. So we have the breadth B. So normally we have unit width. So B is actually 1. Okay, so this is a general expression. So how to solve it? I will upload the guidelines, okay, later on, but I don't have the solution. So if you have the solution, then you can discuss and check. Then I will cross check. Okay, so we need to find out the frictional drag. Fd is equal to 0 to L. We have tau B dx. Okay. Okay, so so we just put the value of tau here again. So what you will get? We sometimes call this FD, sometimes we write FL. L means the length or the drag over the length. Okay, so that should be okay. So we have rho is rho u square, and then integration of d theta dx, and then we have b dx. I just put the value of tau. So if you simplify it, what you will get? Rho u infinity, sorry, you can reuse the u infinity square. What else we have? D theta by dx, you are about to integrate about the x, so this should be this will be cancelled out, right? Over the length, so is 0 to L. So what you will have, we have the b, and we have 0 to L, we have d theta, because dx will cancel out. So if you have this one, so it means that your theta rho u infinity square, then we have b theta L. Theta L means if you have the x in the theta equation, just substitute the x with L. Okay, substitute whenever you have x, you just write L. That will be the expression. Okay, so for an example, example is if you have the theta example, okay, maybe 0.038, maybe you have x, okay, maybe you have the rex to the power 1 over 5, maybe. So if you want to write it as a L, so what you will write? If you put L here, you need to write, in this case, nice free. You need to write capital L, not the X, L. Okay, so if you have this one L, just put the value here and simplify it. Then you will get the result. Okay, and so that's easy. Just shuffle it and then you will get the result. Most of the time we need to express the result in terms of local Reynolds number. This is 1 over 5. This is just an example, don't be confused, okay? Just an example. If your theta is like this, then you can put the values and you will get this. And as I said last time, we have the local frictional coefficient. We have another one, the capital F. F is average skin friction. Average skin friction is FD drag by half rho U square A. Okay, we have this area here is average. Just keep it in mind, okay? Don't be confused with local and average one. So local is half rho square, but when we have the average, we have divided by A. Or sometimes they write in this way. So instead of writing here, they consider divided by A is here. Okay, so I hope you understand at least few things, and I will share the guidelines. Okay, guidelines is here for you to practice, or those who have problem in understanding, you can also use this as a guideline. Tutorial 1. So this one is not showing any result, but it gives you the idea how to solve. Okay, the results are not here, but it says that how to do. Okay, so if you don't have any problem so far, so I need to consider the next example. Anyone want to ask anything?
Doctor,
Yes, please.
will the word notes just now, will you post it?
Word note. You mean the video? Yeah, it's recording, so I will post it. Is under so I will post it. Okay.
What solution? Can you put
Solution? I don't have solution. I am sorry, I don't have solution. Solution I have.
No.
Sorry.
Not the solution, but the scribble part that you did now.
You see?
Uh,
Oh, this one in the video you can find it out. You know, you need this one is just a scratch. So don't believe then that you believe that is true, then you will be in trouble. So you see the video and derive it together and try to find out what is the values. Okay, so as I said, these values are not true. I'm not guaranteed that these are true. I'm solving it right here. Okay, and some values are dummy, just to make sure that you can get the values.
okay, doctor.
Yeah, okay, thank you. Okay, next thing, another question. So explain how the boundary layer are used to define the ship resistance during ship design. So this one already I already explained this one, because we have when we consider the resistance, we have the wave making resistance, we have the frictional resistance. So for the frictional resistance, we need to consider the boundary layer theory. For the wave making resistance, we use the potential flow theory. Potential flow theory, although it's linear, okay, but because potential wave theory or potential flow theory is still sufficient to define the wave making resistance, because by using the superimposition theorem, we can actually create any types of nonlinearity even we have the potential flow. Okay, anyway, so the explanations are there in the slide, so I focus on the tutorial part only. So next thing is say the velocity distribution is same. You can see the similar type of questions is repeated. Okay, so you might get similar type of thing. So the velocity potential in the boundary layer U is equal to U by capital U is equal to Y by delta to the power 1 by 7. Okay, so it said that calculate the using the von Karman integral method. You need to calculate the displacement boundary layer thickness. So boundary layer thickness, you have to find it out. So how to calculate So this one is very famous. If you haven't watched my turbulent the lecture for the turbulent flow, so for the turbulent flow, this is the constant. We call this 1/7 power method. Okay, so u by u infinity is equal to y by delta to the power 1/7. This is for turbulent flow. Normally we consider this profile is like that. Okay, in case of laminar flow, we consider only the relationship is maybe linear or parabolic, ax square plus bx plus c, something like that. But in this case, for the turbulent flow, we have the 1/7 power. Okay, so let's try to solve the boundary layer thickness using the von Karman integral. Okay, so similar way, von Karman integral, you already know that the tau in this case is rho u square d theta dx. Von Karman integral, this form is actually true for whether you have 0 or whether you have w. Okay, so this is true. You can put this one is 0, and you can also consider when it is any position. Okay, so not necessarily we need to put the 0. So normally we consider is w. Is actually the concept is same. Okay, when you need to find out the boundary layer thickness, always we need to use the two form. One is Blasius form, another one is von Karman integral form. Both are for the shear stress. Then we equate this equation, these two equations. So in this case, again you need to calculate d theta by dx, as I said before. So I'm using the von Karman formula, integral formula. Okay, so in this case, d dx of you will have integration of 0 to delta. Then you have u by capital U. I am putting the value of theta. So 1 minus you have u by capital U, dy. Right. So in this case, you have u by capital U square. So I can put the u infinity to make the things consistent. So d dx. Then what you will have 0 to delta. You know, most of the time where the student do mistake, they do mistake in the integration and simplification. So this one, and then multiplied by 1 minus y by y delta to the power 1/7. Okay, so then we have the dy. I don't have the space here. So now if you do the integration and simplification, what you will get? You will get rho u infinity square d dx. Try to find it out. Okay, you should get 7/72 delta. Some constant, you will always get some constant, sometimes 1/15, whatever, something, whatever it is. It depends on the expression that you use. In this case, we are using u by u infinity is equal to y by delta to the power 1/7. So you have different types of expression. I might give different types of expression, different parabolic, or I can give also for the turbulent flow. So you have to use this one. Okay, so if you have this one now, I must mention one thing, that when is given for the turbulent flow, okay, and if it is mentioned that in turbulent conditions, so I'm not sure whether they mention it or not. This one done. Hold on, I need to check the question. Okay, so you have to understand that this boundary condition, okay, if you have this boundary condition y by delta to the power 1/7, that is for turbulent flow, whether it's mentioned or not. If you go through my lecture for the turbulent flow, you will understand from the velocity profile. So now you need to understand that this one is true, is okay. For the Blasius form, when we write last time what we wrote that tau naught is equal to we have mu du by dy, right, at y is equal to 0. Then we equate these two equations, if you remember. That is okay for when the relationship is what can I say, linear or parabolic. But when you have the turbulent flow, that is, if you see the relationship is 1/7, it means u by u infinity is equal to y by delta to the power 1/7. You must use another form, that is the Blasius law of viscosity, Blasius form. but this one is for turbulent flow. So you need to note it down, this equation. Please note it down. 0.0226 rho u square, that is u infinity square, and then you will have mu, and you have rho u infinity delta to the power 1 by 4. Again, I'm saying the same. So please highlight this equation because you must know this one. This is the boundary layer condition, or when you have the turbulent flow, you need to use this equation. This equation is known as Blasius law of viscosity. Okay, so Blasius law of viscosity. So only we will use this equation when you will see that your relationship is y by delta is equal to like to the power 1 over 7. So that is the turbulent flow. You cannot use for the laminar one. Okay. So because we have the turbulent flow, we are no longer using the knot. Okay. So at y is equal to 0 is not applicable in this case. So just you need to differentiate these two. So now you have this expression. So for what you can do, now you do the same thing. Left hand side is equal to right hand side. Okay, so left hand side in this case, now in this case fortunately you don't have any derivative term, so you no need to do anything, just equate the things. So u rho u infinity ddx of 7 by 72 delta should be equal to this value, right hand side 0.226. We have the rho u infinity square, and then we have mu rho u infinity delta to the power 1 by 4. Okay, so you have already the things there. So what you need to do, again you need to do the integration, right? So if you do the integration here, integrate left hand side and right hand side, what you will get, this integration and this will be cancelled out. You will get rho u infinity square. This should be cancelled out. Okay, it's better I cancel out. So what you will have, u rho will be cancelled out, u infinity square will be cancelled out. So what you will have, then you will have only 7 over 72 delta, right, is equal to you will have 0.0226, and then to the power, in this case you will have this value is constant, rho mu u infinity delta to the power 1 by 4, and then multiplied by x, because you are differentiating with integrating with respect to x. So you will have extra x here. So I don't know where I missed out in my previous definition of x, so please take care of that. Okay, or maybe I was correct, so please rejudge the things. So you have this one 7 over like something, whatever it is. So again your target is, remember that you need to make the rex. Okay, and you have the delta to the power, this should be 1 by 4. Okay, it's not 1 by 2, it's 1 by 4. My writing is don't have enough space. So if you make the reshuffle the things, what you will have, so what you will have, we will have 7 over 72, you have delta, and then in this case we have delta to the power 1 by 4, right? And on the other hand we have the 0.0226, whatever we have the extra thing, mu by rho u infinity, delta is already taken into account, and then we have the x. So in this case you will see that we will have delta to the power, yeah, anything want to say? Integrating, yeah, you can put the integrating constant c, but later on if you put the boundary condition, then you will see that most of the time the c is 0. So in short, you just ignore it. Okay. So you can check, you put and then put the values, you will get the c0, or integrating constant should be 0. So here you can see where is, okay, here, so it's 1 should be somewhere. Okay, is not divided by. Okay, you have to let me correct. Okay, you see I did the wrong thing. Is on the below, right? Delta to the power 1 by 4, so it should be multiplied, not divided by. So it should be delta to the power 1 by 4. So in this case what you will have then, so somehow maybe I can do mistake. Okay, please readjust the things. So 1 by 1 4, and then we have the 72 by 7, and then multiplied by 0.0226. So how much it becomes? 72.0.0226 divided by 7. Okay, so, and also we have more thing, so it should be to the power 5 by 4, right? 5 by 4, and we will have the constant, and you have the x, and also we have the value is like something rho u infinity 1 by 4. Okay, hold on 1 minute. So after you simplify the things, if you want to get the delta, you can find it out. The delta at last you will get something like that, 0.371. You will have x, then this one will be r e x to the power 1 by 5. Okay, you will get this. Okay, so of course you need to do some simplification, you need to do some adjustment in the parameter, because if you need to go inside x to the power 1 by 4, you need to multiply it by x to the power 1 by 4, right? So what you will get then at that time, you need to think about it. Okay, so I'm talking about this part, I'm talking about this part. If you want to write it in rex to the power 1 by 5, so what you need to do, so you need this one, right? In this case you should have mu by rho is nu, so you should have this one. Oh, okay, hold on. So you should have nu, and you have u infinity, you should have x here, right? And in this case you have your if you want to make it 1 over 5, you need to put it 1 over 5 here. So you need to adjust the x here in this case. If you put x, and then you need to adjust this x. Okay, so this part is for you. How to get this one? You try to derive it. In short, at last you will get this one. Okay, these are the algebra. So this is the way we can get, and you know that the rex in this case is u infinity x by nu, or you can also write rho u infinity x by mu. You already know that. Okay, so that's how we derive the delta. So I just continue. So what else we need to do? We need to find out the shear stress. So now is all related. Okay, now you have the shear stress. So shear stress, you know the expression is according to this Blasius form, 226 rho u square, and then you have the expression here 1 over 4. So you have this rho u, so you just put the value of delta. You need to put the value of delta, in this equation. Okay, in this equation means in this equation. Okay, you just put the value of delta and then you will simplify it. What the result, the expression that you will get, I am writing it down for you, 0.0576. then you will have rho u square, and then we have 2 rex to the power 1 by 5. Okay, so you just, after you got the delta value is already there, I already mentioned here, so you need to put the value of delta and then you will get the result. Okay, so note is put delta in TW Blasius form, Blasius equation. Okay, then we will have this expression. Okay, so this is easy, just you put the values and then when you practice a few times then you will used to it. Okay, so it's not actually difficult, you will see the same thing is coming. It means you need to make the rex, so you need to practice first of all, then you will see that you can easily convert this rho mu and relationship by rex, then you need to adjust the remaining. Okay, so we do some simplification here. The next thing is we have local coefficient, local drag coefficient, and we also have the frictional drag coefficient. So local drag coefficient and frictional drag coefficient. Okay, so again the drag coefficient, you remember that this one is related with tau, all are same. Okay, so what you need to do is very simple. So CF should be you have this tau W divided by half rho u square, or that is u infinity square. So just put the value of tau in this case, so you will simplify it in this way. So rho u square will be cancelled out honestly, and you will get 0.0576. So all are related. Okay, once you get the delta, then you get the tau, and if you get the tau, then you can get the CF, just substitution. So make sure you calculate the delta properly, and then you have the tau, then after that you will get CF. Okay, and this is a local frictional coefficient. Then we have the frictional drag, capital. Okay, not local, is capital total drag. So in this case CDF, we use the drag. So before we use the stress, in this case we use the drag. So this one is equal to actually FD or D, whatever you like you can write. So this should be half rho, if you remember it should be A u square. Okay, we have the A. So this FD you need to calculate. FD you need to calculate, but FD you already know how to calculate. FD is actually integration of tau, right? B dx. Then if you have this and you substitute the value of tau, what you will get 0.0576. You have the rho u infinity square, and then you have the u. In this case you will have RE. Okay, so because you need the L in this case, I write the X first. So you will get rho u infinity X divided by mu to the power 1 by 5, and then we have the B dx, right? So now you need to integrate it. So as I said before, you just change the X with L. So in this case rho u infinity square, so it's okay. So in this case 2, instead of writing rex, now you need to write rel, because your x will become L. and we have the b, and dx, integration of d dx is l x, and then l minus 0 should be l. Okay, so if you have this, and then if you substitute this CDF should be after you simplify this, I think you will get something like 0.072, and we will have Rex to the power 1 over 5. It means that this coefficient, and you have this one, right, half, so it will become 2. So if you see this 0.576 multiplied by 2, and we have some additional part. Yeah, so other things, we have the u infinity, this will be crossed down because we also have the rho u infinity, upper and lower part, and we have the b and l. This one represent the area, that will be also cut down. Okay, this actually represent the a. What else we have? I think that's okay. Divided by, or I just make it multiply 0.5762. Sometimes I'm not sure the coefficients, okay, but just do your calculation. Sometimes it's wrong, sometimes I'm not sure. I'm just referring to some other calculations. So please try to find it out. Just put the values and simplify it. Whatever value you will get, that will be the result. Be confident, okay? So this one should be, you just put it here. Oh, this one you have the 2, okay, that's why. Then multiplied by 2. 0.0, I'm just checking the values are okay or not. 0.576. This divided by 2. This one already have. Values are not close. You cancel out. Anyway, you just carry on the things, okay? I will check whether your calculation is okay or not. Please try to solve these problems, and if you found any discrepancy, your values are not getting there, so let me know. But that is the way we solve the problems, okay? So basically what I am going to tell here, most of the time you need to find out the delta, okay, and in this case this is a turbulent flow, so we have the special equation for Laplace form. Otherwise we will use the same equation for the y is equal to 0 form, but main thing is you have to balance the two forms, and then from there you will get the delta in terms of x, okay, and then you get the what can I say, you need to calculate the stress. So in the stress equation you just put the value of delta. If you have the tau stress, then you can divide it by half rho u square, then you will get local coefficients, local frictional coefficient. And if you want to find out the total frictional coefficient, you need to find out FD. In that case you need to integrate this one and then put the values and then simplify it. Okay, even you follow the expressions, the procedures, even your calculation is wrong, you will get of course the partial marking, but make sure your formation should be like this. Your formation should be like this, and you need to be familiar with that, okay? Okay, so you can see that try to practice these kinds of problems with different expressions. Okay, you can see the tutorial already in the slides, so you can practice those things. So another one said that, so velocity distribution, okay, in the boundary layer is something like that. The velocity distribution for this, okay, so theta is already given to you, okay, and then you need to find out this expression. It means the ratio of displacement thickness to the momentum thickness. So how to solve this one is easy, okay? This one not is always are not like complicated. This one you might get maybe 15 marks or something like that. How about this one? So it's already given. Sometimes the expressions are given to you. Delta star is 0 to delta, you already know, 1 minus u by u infinity dy. So in this case, your expression already given. So y by u by u infinity is y over delta to the power 1 by 5, right, dy. Then integrate it, simplify it, you will get 1 over 6 delta. So it's something like that you already calculated before. So delta star by delta is equal to 1 over 6. Okay. So this equation haven't used it here. So how about this one? Oil with velocity of 1.2 meter per second across the surface of a flat plate with 3 meter long and 2 meter side or wide. If the density of the oil is 860 kilogram per meter cube and the kinematic viscosity is this much, based on the velocity distribution, determine the drag force acting on the surface. So some informations are given. Mainly you need to calculate the drag force. Okay. So how to calculate? So again, remember that what are the things are given? Cross-sectional area already given. Velocity is given, and then we have the length given, width given, the viscosity also or density also given, viscosity also given. You have to find out the drag. So it doesn't matter you have the oil or any different types of liquid, so it doesn't matter. So you need to calculate the drag force. And to calculate the drag, you know that what you need. The drag is actually integration of this one, right? B dx, or you can write del A. So you need to know the tau in this case, right? So if you want to use the blast, we will use this von integral form. So that one we can write rho u square integration of d theta dx and then dA. So you need to find out d theta x, right? So this one we can simplify it like before. If you remember, this one is actually nothing but d theta dx, and instead of writing dA we can write b dx. Okay, so in this case what we will have rho u square b, and then we just dx will be cancelled out, same like before. Okay, so what we will have theta L, right? If you remember, or if you don't remember, just write 0 to L, in this case d theta. So in this case we are integrating 0 to L. So it means that what we will have rho u square, then we will have b, and then if you integrate this 0 to L to theta, you will have theta, and then we will have theta L. This expression we already derived before, rho u square bu theta L. You can write the expression directly also, okay, no problem. So what you need in this case, you need the theta L. That's the thing you need. Okay, and what else? Rho already given, u square already given, your breadth b already given. What else we have? So just you don't know theta L. Okay, so theta L, how to write the theta L is very simple. You just write down the value of theta, you just calculate and just replace the x with L that I said before. So if you are wondering which theta you should use, the theta already given in here in the expression here. So theta will be already given in the form of L. So just put the value here, very easy. So your theta L will be is given 0.038 L divided by REL 1 by 5. But what you don't know REL, right? So we know REX. So REL should be rho U infinity L by mu, or you can write it UL by nu. So your U velocity, so in this case, sorry, it is U infinity, right? So U velocity is given 1.2, and then length is given 3, viscosity is given 1.2 10 to the power minus 5 or something, whatever it is. So you just get the value, and if you get the value of REL, put the value here, and you already know the L is 3. Okay, so after you get the value theta L, just substitute the values here. So in short, after you do all the calculation, you should get FL or FD, whatever you like, you can say, is 22.67 watt. Okay, so I think that's okay. Do you have any questions? No. Are you there?
Yes.
Okay, so just hold on for a few minutes more, because these topics, you just solve the problem, but you also need to watch the videos. Okay, so probably honestly, but if I take the quiz, I don't know whether how you will get the response. So what I can do, I can take the quiz at the beginning of the next week. Okay, that's the thing I can do for you at the beginning of the next week. So by this weekend, you must study the content. At least you need to go through the videos. Okay, so to understand the contents, no need to go for the derivation, but just keep an eye how I derive and how these things are related. If you think these equations are important, just note it down, and then also try to solve this problem. This will give you the confidence. Okay, you have to solve the problem. That's why I'm not solving it fully. I'm just giving you the hints. Okay, and make sure your answer is matching. If it's not matching, let me know. I can cross check. Okay, so this is a type of problem that you can get. Okay, then others like this also have one problem, but it's different type. So a barge, it said that a barge 40 meter long, okay, and 2 meter draft is towed at a speed of 5 meter per second in a river as shown in figure 2. By using the momentum thickness theta L already given, the REL is already is the Reynolds number at the tailing edge of the plate, and taking the barge surface as a flat plate, calculate the force required to overcome the frictional drag. So force required to overcome the frictional drag, it means that you need the frictional force, the drag force at the bottom of the surface of the barge. So your density, rho, density and dynamic viscosity already given to you. So how to solve this problem is same problem. So whenever you said that calculate the force or something like that, so you need to use the same equation. Okay, so FD drag in this case, same like before, as I said, there's a, and then when you solve the problem you will see, oh, this is the same thing, just at an instant you can write it down. So you have the rho u square, you have the b, and you have dx will cancel out, 0 to integration L d theta. So you will theta, and you will need to write theta L, right? If you put the u infinity, that we have the theta L, but theta L already given to you. So it's very easy, the like same problem. So if theta L is already given, so you have 0.035 L divided by REL, but you don't know REL, so you have to find it out. REL, so sorry, this should be 1/5. So REL, again I'm saying the same thing, rho u infinity L by mu. So you already know rho value, you already know the velocity 5 meter per second, you already know length, already know is the length is given 40. Yes, 40 meter long, and the value of B already know. So in this case the B is the cross section area, so in this case B should be 10. Okay, so width is already given, so all the values are given mainly, so you can calculate the value and you will get the expressions for FD. And this one you will get the FD is in this case 4642.05 Newton. Why it said ton last time? What I said, maybe I pronounced wrongly. Oh, I said what? I sorry. This should be ton, Newton, not ton. I said what, right? I don't know why I said. This should be in Newton. Okay, and force, not what. Not is a power. Power is what is okay. So force should be in Newton. Okay, so any more problem it has? No. So basically, make sure you can calculate these kinds of thing. This. Okay, and sometimes it asks you to calculate the drag force. So then you use the same formula. This one probably will be given to you. This is easy one. Okay, so this one also the boundary layer thickness is also easy. You need to. This is from Blasius. This one is for von Karman. Integrate, then you will get delta is a function of x. That's all. If you have the delta, in the tau expression you just put it back, then you will get shear stress. If you have the shear stress, then you just divide it by half rho a u square, then you will get local friction coefficient. If you want the total drag, so you need to find out FD first and then divide it by half rho a u square. Okay, this is very simple, but thing is you need to play with the tuning, I mean the formation of REX. You just need to shuffle the parameters and do some tactics, okay, so that you can get the desired form. So if you just substitute the value without any meaning, then there is no way. Of course you will get some marks, but you must represent in proper way, something like that in the form of RE. Okay, so that's all for today. So as I know that I feel that you need to practice, and I'm not sure how many students have watched the video, so I want to give you the time. This is third week, should be okay. So once you overcome these things and you already learned these things, then we can take a quiz 2 and 3 together, should be okay. Okay, so time will be, I can adjust the things. So I don't want the students to just attempt the quiz and get 0 or get 1. Okay, so I just want the students to get a very good grade for me for this course. Okay, so I will, okay, so this I just stopped the recording.